So today we're talking about set and Venn diagrams. Now this is a topic which has already come up in GCSE, but eventually, hopefully, it will get slightly harder when we talk about the IB version of it. The good thing is you already know at least some of this, so you won't have an issue with the introduction. Today we're going to start with the introduction to sets, and more specifically we're going to talk about some linguistic ideas, some language and notation we use. So one very important thing that we have to talk about is the notion of a set. This is a relatively new thing in maths. It hasn't been around for more than a couple of centuries, so it's a really recent thing. I'd say mostly the last century it's been developed, really. A set is a collection of different things or numbers, and each thing or number is called an element or member of the set. Then we've got some notations. This it looks a bit like the Greek letter epsilon, which means this belongs to or is an element of. And then, for example, if you have a set down here, you've got the 11 is an element of this set. So we put 11 and then this little epsilon, and then we put this letter of the set. So that's the idea with this notation. Then if you put a line going through this epsilon, then it means it doesn't belong to, it's not an element of. So for example, if you look into this set, you see 15 is not really an element of this set. So you would say 15 is not an element of this set, P. Then finally, this N stands for number of. So N of A means how many elements do you have in set A. So for example, here we have 1, 2, 3, 4, 5, 6, 7, 8. So we would say N of P, which is this set, is equal to 8. So N stands for number. Right, moving on, we've got a couple of definitions and then an example, and we will get started. So we say that two sets are equal if they contain exactly the same elements. So you need to have two sets which have exactly the same elements, exactly the same number of elements. That's the only case when they're equal. We say that a set A is a subset of set B if basically all of the elements of A are inside B. So for example, if I said the set A is the set which has the numbers 1 and 2, and set B is the set where we've got 1, 2, 3 in there, then we say that A is a subset of B, because all of A is included within B. If you want a graphical representation of it, then you have a big circle B, and then inside circle B, you have circle A. So that means A is a subset of B. It's a little circle inside B. Now, we've got a different special word here. A proper subset of B is basically when we know for a fact that the set A doesn't have all, it's slightly smaller than set B. So what does it mean? It says here when A is definitely not equal to B. So obviously in this case up here, I should correct that to, now that I've shown you this notation, A is actually a proper subset of B, because we know for a fact we only have two elements here, whereas here we have three elements. So definitely A is a proper subset of B because it can't be equal to B. But often, because when we talk about set theory, we don't really know for a fact a set will be a proper subset of B. So we put the little line underneath just in case it happens to be the same, because we never really know if it might actually include all of the elements of B eventually. So yeah, let's keep this in mind. It's a bit like having less than or equal to, it looks a bit like that, or less than, strictly less than. So keep this in mind, it is like related. These are cousin kind of notations. And then moving on to the empty set. Now this is a relatively new thing. Imagine 0 was, it hasn't existed for more than 200 years. The empty set has existed for even less. So people had a bit of an issue with this notion when it first came to be. Somebody came up with this notion and said, oh, imagine a set which contains nothing. Most people went like, what do you mean, a set which contains nothing? This is a very weird thing. Stop talking to me. So this idea of the empty set is a bit more elevated. It requires some thought process, So it's a set which contains nothing. Okay, so imagine an empty box, an empty drawer. So this is the empty set. It's an important thing in set theory because we use this to construct everything else in set notation. Okay, moving on to the next bit. A set A is a finite set if basically it's got a specific number of elements. So it's not infinite, really. If it's infinite, you would call it an infinite set. So for example, if we say the set A, which contains 1, 2, the numbers 1, 2, then obviously the number of elements in A is 2. So it's actually finite. So A is finite. But if I were to say, well, imagine the set of real numbers. Well, this is all the numbers we know. So it's actually basically an infinite set. So this is an infinite set. Why is that? Because we know that the number of elements in the real numbers is actually infinite. So that's the idea. Okay, let's look at an example. How does this all come to be? What do we need to do really practically in action? So if they give you, for example, a set P, which is all the letters in this word, amateur, so the way we would actually write that is we would use curly brackets and we would just write them down like this, A, M. So let me show you something interesting here. A, M, A, T, then E, then U, and then R. So when we do this, this is actually wrong. Because we don't want to list the same letter twice. So I'm just going to go ahead and cancel this. I'm going to get rid of this. It's fine to do this, start by writing them all down, but then we don't need to do it. It's like talking to somebody and saying, oh, I've got red clothes, I've got green clothes, oh, I've got red clothes as well, and I've got blue clothes. So you wouldn't actually list them twice. That's why in set notation, set theory, we don't actually list something twice, just list it once. We don't need to list it twice. And then set Q, so this is set P. The first one is set P. Actually, it's been done for me down here, so I'm going to stop writing that. So this is how we wrote set B. That's why we skipped the second A. If you do the same thing for Q, you list Q like this. You use curly brackets for it. That's it. That's part A. List the elements of P and Q means just write this down, making sure you don't list duplicates, like it says here on the right. Moving on to the next one, write N of P. What is N of P? Well, it's just the number of elements in P. And obviously, if you had made that mistake of listing A twice, you would actually get this wrong. So keep this in mind, do not list elements twice. So here, just count 1, 2, 3, 4, 5, 6. Number of P is 6, the number of elements in P. Number of elements in Q is 4, obviously, so you just say 4. Just a note here, the number of elements in a set is often called the cardinality of the set. So just in case you ever come across this, this is what it will be. And also, you might come across this notation, vertical bars on each side of the set. So this is the same as N of A, in case you ever come across this on Wikipedia or a textbook or a question. Right, moving on to C. So we've got some questions here. Basically, this is us practicing this notation we've seen today. This means U is an element of Q. So this little epsilon, I'm just going to remind you here that this means is an element of or belongs to. So it's an element of Q. So let's establish whether U is an element of Q. So U, the letter U, is it an element of this set Q? Well, no, it's not. So we can say that this is false. So the first statement is false. Let's move on to the next one. So this R is not an element of Q. Well, we look inside the set Q. Do we have an R in here? No, we don't have any R's. So we can say here, this is actually true. Indeed, R is not an element of Q. So basically, I'm going to make a note here, not an element of. That's what that means. And I'm going to upload these annotations in a bit on Google Classroom. Third one, P is a subset of Q. So let's check, is this entire set P, inside the set Q? Well, clearly not, because, well, this one has more elements than Q, so definitely not. So basically, this is false. And I'm just going to refresh your memories here. It means a subset. Okay, and the last one is like the notation of subset, but it doesn't have that little equal line underneath. So this is actually a proper subset, which means it's entirely included in the other set. So let's see, is set Q, which is this set here, entirely included? Is it a proper set of, as a proper subset of set P? Let's see, T is inside, so let me start underlining. So T is indeed inside P. E is indeed inside set P. A is indeed inside set P. And then M is indeed inside set P. But because set P includes more letters here, more elements, indeed Q is a proper subset of P because it's entirely included in there, but it's not actually equal to P. So yes, indeed, it is a proper subset of P. GP. And that's pretty much what we are doing today. This is just an introduction to this unit, to this theory. Now I'm going to stop recording here, and I'm going to give everyone the chance to ask me questions if you want to.